All right, so as a person aspiring to be a chef, today I'll be talking about cocktails, and actually specifically molecular cocktails. And this is maybe the dry version of what the title slide looks like, but I would really like you to think about it in this way. Okay, so stay in this, bar kind of atmosphere, and we're going to try and understand if we can actually make some sense of the different ingredients that we can typically find in cocktails, and if maybe these types of molecules, because as you know, matter is made up out of atoms and molecules, if actually these molecules can already be formed in very, very early stages of star formation, or phrased differently, in stellar nurseries. Okay, so this is a way that I like to think about astrochemistry, which is by thinking that actually what we are doing is chemical archaeology in space. So what we see depicted here, yeah, perfect, that works. So what we see depicted here is a very nice artist impression of a kind of life cycle. And I recognize many faces here, so on the off chance that there are people here who've never seen this before, right? I will walk you through them briefly. So what you can see here is eventually, if you follow the arrows, you can see something that you maybe recognize, right? This is a star and a planetary system surrounding that. And the way we like to think about that is that there are these different stages of the evolution of star and planetary systems that starts out with very low density, increasing density, until eventually at the core of what we call a cloud or prestellar core, a protostar is formed, disk surrounds that, and in that disk, planets can be formed. Okay. So now what I am particularly interested in is understanding the chemistry that takes place in the very early stages. And for me, the reason is that if we know the ingredients at the start, we can also sort of build on that and try and understand, okay, now we know what we have as input here. Now, how do these molecules actually continue to either form or change along the course of the star and planetary systems? So what I like to focus on are these, let's say, these dense regions here. And this is also where the on the rocks part of the title comes from. So actually what happens is that especially in these stages here, at the core of the either cloud or prestellar core, the temperatures are very, very low. And that means that whenever you have a surface, atoms and molecules can freeze out onto that surface. Very similar to what happens to your car when it's outside in winter and you want to, rush to work, but actually you can't because there's a thin layer of ice covering your car window. That's essentially what happens in space as well, except the time scales are a little bit different. Okay, so what I'm interested in and what I'll be talking about is the chemistry of small molecules that adsorb on the surface, on a very, very cold surface, meet a reaction partner, and then continue to form other molecules. All right. Okay, so let's start simple and maybe, not too alcoholic yet. Okay, so let's have a look at a, virgin cocktail. So very, very plain, just a formation of water, the formation of water ice. So I'll walk you through this example, but then when we get to other molecules, maybe there can be some input from you. What do you think if I give you the ingredients, which molecules can form? But here I'll do it the other way around. So for water, the ingredients that we need are oxygen atoms, hydrogen atoms, or actually hydrogen molecules. Okay? So these are essentially the possibilities. That's what we start out with. And as I said before, a very important component here is the grain surface. So tiny little dust grains that we consider eventually maybe, rocky material, but they start out as being very small, so maybe micron-sized. Okay? So these are the ingredients that we have. So how can we imagine that the chemistry then takes place? So the way that we tend to think about that is shown in this video. Now let's see if that works. can you maybe press the button? I see that's probably not going to work. So can you help me? All right. Because I need someone to hold the mic. Okay, so now what happens is that when we have a surface of a grain, and an atom or molecule lands on one side, and maybe, let's say, a day later, another atom or molecule lands on another side. Okay? So we have these two species here. It can be either be two atoms, or it could be an atom and a small molecule. Now, I was talking about water. Okay? So what we have are oxygen atoms and hydrogen atoms. So let's say this is an oxygen atom, it's a little bit more heavy. This is a hydrogen atom. So what happens is that the oxygen atom will just sit here happily, but the hydrogen atom will scan the surface of the dust grain until eventually it sits next to the oxygen atom, or any other species, but in this example, oxygen and hydrogen. And then when they are next to each other, then that's the moment when a chemical reaction can take place, and you can actually form OH. So this is the first step towards water formation. Okay, so we have here OH, and now I need a third hand, so could you lend me your hand? Yeah. So now there's another hydrogen atom that comes in, scans the surface, sits next to the oxygen, and then this is how we can form water. So H2O, right? Thank you. Okay, so this is how we form water. Okay, and there can be many different reactions. Now I showed you we showed you one example, but we can also have formation of water with H2, or when two oxygen atoms meet each other, we form O2, and then that can be hydrogenated, and so on and so forth. All right, cool. So we've learned that when we have oxygen atoms and these ingredients here, we can form water. Okay. Now, if I give you another ingredient, if I tell you that actually besides oxygen atoms, we also have carbon atoms, and again, these ingredients, can you imagine which molecule can be formed? Methane, I heard methane, very nice, exactly. So it's the same type of process. So the carbon atom and hydrogen atoms come in and they hydrogenate, that's the word, hydrogenate the carbon atom. All right, and what about nitrogen atoms? Ammonia, exactly. So these are types of molecules, so small molecules with a lot of hydrogen atoms are molecules that actually can be formed on very, very cold surfaces under conditions as they are in the interstellar medium, and maybe later we'll see whether actually we can see them in interstellar, in astronomical observations. Okay, so let's move away, let's take one step further, move away from water, and now go to another component or another molecule that we tend to find a lot in interstellar space, which is carbon monoxide. So you might know this molecule as a very poisonous one, and one that we have detectors for, and that you should be very careful in inhaling, which all of that is true. So that's why I figured, this is probably a little bit lethal. Now, instead of starting out with atoms, we start out with carbon monoxide molecules, and again, we have these ice-covered dust grains. Okay. So here we have carbon and oxygen. Okay. All right. So now slowly we start to add more complexity. Okay. Okay. So what can we do with this carbon monoxide? So this is still a mocktail, right? This is still a non-alcoholic species. So let's see if we can make it a little bit more interesting and actually make a small alcohol. All right. So we start with carbon monoxide, and we have these hydrogen atoms. Then the hydrogen atoms, very similar to what we just showed you, they come in. And when they eventually meet the reaction partner, they can react. Maybe some of you already recognize this molecule here as formaldehyde. we can actually add more hydrogen atoms. And now, for the trained eye, you can already imagine that actually what's depicted here is methanol. Okay? So methanol is not quite the alcohol that you're maybe consuming now, luckily. This is very poisonous. But this is actually the smallest alcohol. So chemically speaking, this is the smallest alcohol that we can find. And this is actually a molecule composed out of 6 atoms that indeed can be formed from the same way of adding hydrogen atoms on a surface. Okay. Now there's another component of cocktails that that makes it usually so delicious to drink, which is that cocktails are typically sweet. Oh, right. Very good. Thank you to my former self of reminding me. So there are actually multiple ways of forming methanol, and Melissa is going to come back to that later on. Okay, so we actually want to understand the complexity of how complex molecules can actually become under these conditions. So for us astrochemists, methanol is essentially already a fairly complex molecule. It has 6 atoms. Like, wow, we made something really cool. It's actually even an alcohol. But when we talk to chemists here on Earth, my colleagues at the chemistry department, they'll say that glucose it's a very simple molecule. So just to give you this perspective. But actually, the ingredients are very similar, right? We have hydrogen, carbon, and oxygen. And it's the same in glucose, hydrogen, carbon, and oxygen. It's just a slightly different way of rearranging them. And that actually means that when we have these types of starting materials, we can indeed actually move towards formation of simple sugars, which has also been demonstrated in the laboratory, and I think with one observation of what we could call a sugar. All right. Now, so far, I've been talking to you about chemistry. And the time scales that are relevant for chemistry are very, very short. So they are maybe between microseconds and seconds. Okay, so for 2 species to sit next to each other and indeed do a chemical reaction takes place on very, very short time scales. Whereas let's say, hydrogen atom accreting onto a dust grain, that's a process that takes place maybe once per day, once per week, once per month, depending on the abundance. And telescope lifetimes that ranges somewhere between years and decades. But the processes that we are interested in are actually on extremely long time scales, right? So millions of years. So how can we bridge this gap between knowledge that we obtain from, say, chemistry, to something that actually is being observed? How can we understand these very short time scales and link them to the very long time scales? And a very typical way for us, at least in astrochemistry, to think about that is by thinking of this triangle. So we have physical chemistry on one edge here, and astronomical observations on another. And actually what's very, very important are astrophysical and astrochemical models. So it's really these models that allow to bridge the gap in time scales and actually also in length scales. Okay. So in terms of the physical chemistry, I've explained a little bit about chemistry to you. But actually, some of these reactions can indeed be done in the laboratory. And there is one such laboratory here in Leiden. There are many others across the world. But in Leiden, there's the laboratory for astrophysics at the observatory, where this is one of the experimental setups. Now, I won't walk you through all the details, obviously, but I would like to show you a sort of simplified animation. So instead of having a dust grain, carbonaceous or silicaceous, we have actually a gold-coated substrate. And then we do something very similar as in the interstellar medium, namely you take molecules and atoms, and you let them hit the surface. The surface is very cold, so they stick, they form an icy layer. Some chemistry takes place, And then we can make use of infrared spectroscopy to actually probe what happens on these surfaces. So just to remind you, in case you forgot, this is essentially where, this is the cocktail that we are making here. And we can use infrared spectroscopy simply to see which molecules have we actually formed. Okay. All right. So to sort of like, summarize that aspect, actually what we see is that there are many different processes happening at the same time, or in very, very short time spans, shortly with respect to each other. So atoms and molecules freeze on the surface, they diffuse, they react, they can evaporate again. It's actually very difficult to experimentally constrain exactly how fast which of these processes happen. And this is where another aspect of physical chemistry comes in, which is computational chemistry, which is what I love to do. And so I'll leave this up for you to read. I'm going to guess most of you can read it. So in case, it says, our field has been struggling with this problem for years. Struggle no more, I'm here to solve it with algorithms. But actually, even so, this problem is really hard. So we try to solve these processes, individually, one by one, computationally, and then link that to experiments, and together that can actually provide input for astrochemical and astrophysical models. And just to give you an example, is actually, so this is a recent example from the last 2 years, where in fact we've looked at the formation of methane, starting out from carbon atoms, and in this case molecular hydrogen, so H2. This was a combined experimental and theoretical work. And then we gave our results to our colleagues who do astrochemical models, who actually implemented these reactions in their model and tried to see, okay, now what have we learned and what changes, downstream from here. So that's just to give you a feeling for how physical chemistry can sort of tie into astrochemistry. And with that, essentially now comes the part of the triangle which moves towards astrophysical observations, right? So astronomical observations. And but that's not my expertise. That will be Melissa's expertise. So keep in mind this image here. You may see it again, most likely. And with that, I would just like to leave up this statement that at least for me, cellar nurseries are a unique chemical playground. And thank you for your attention.
Are there questions for Thanja?
You mentioned in this beautiful demonstration that you did, you mentioned some of the atoms are walking around the dust specks. How big are they in comparison? Because it sounds to me like it's an ant walking over the Earth.
Yes, so the dust grains themselves we think are roughly have a diameter of maybe up to a micron, and the size of an atom or molecule is maybe a nanometer.
So 1,000 times less? I'm sorry, I'm not familiar with
yeah, so it's a diameter, so you'd have to convert it into surface area if you wish.
Approximately.
Yeah.
I was wondering about the grades themselves. You mentioned the grades several times. Are they usually silica compounds, or as you referenced rocks? So, okay.
Yeah.
Are these like so? What you study in these ices? Is this what they're called volatile compounds in chemistry?
I guess so,
grades
yeah.
are more like non-volatile.
Yeah. So there are different ways to think about grains. At least silica features or silicaceous grains are very typical to imagine. So in case you're familiar with minerals, it's a phosphorite. Yeah. So it contains silicon, oxygen, magnesium, and over time, so over the lifetime of a cloud, they get covered more and more by atoms and molecules, which essentially coat that little grain with a layer of ice. And so in the beginning, the first few atoms and molecules that sit on that grain, they still feel very much the mineral surface, but with, as time progresses, you create an icy layer, so whichever molecule lands afterwards actually feels an icy layer rather than the refractory material underneath.
So just a quick follow-up question. So that means that most theories suggest that first the non-volatile elements clump together in these silicate, non-volatile grains, and then the ices come afterwards. Is that confirmed, or can it be just...
These grains come from, let's say, leftovers from previous dead stars.
Oh, not the same cloud. Okay. Yeah. Okay, I understand. They were formed before.
Yes.
Yeah. I understand. Thank you.
If there are no other questions, let's thank Thanja again.